Wave nature of matter. The wave nature of light is exhibited in the phenomena of interference, diffraction, and polarization, whereas in photoelectric effect and Compton effect, radiation behaves as if it is made up of a bunch of particles, the photons. If radiation has a dual wave-particle nature, might not the particles of nature, the electrons, protons, etc., also exhibit wave-like character? In quantum mechanics, the concept of matter waves reflects the wave-particle duality of matter. The theory was proposed by Louis de Broglie in 1924 in his PhD thesis. The de Broglie relations show that the wavelength is inversely proportional to the momentum of a particle and is also called de Broglie wavelength. Wavelength lambda associated with a particle of momentum p is given as lambda is equal to h upon p is equal to h upon mv, equation 1, where m is the mass of the particle and v its speed. Equation 1 is satisfied also by a photon. For a photon, as we have seen, p is equal to h nu upon c. H upon p is equal to c upon nu is equal to lambda. Equation 2. From equation 1, we get that lambda is so small for a heavier particle, large m, or more energetic particle, large v, that it is beyond any measurement. That is why macroscopic objects in our daily life do not show wave-like properties. De Broglie didn't have any experimental proof at the time of his proposal. It took 3 years for C.J. Davison and L.H. Germer to observe diffraction patterns from electrons passing a crystalline metallic target. For an electron, mass m, charge E, accelerated from rest through a accelerating potential V. The de Broglie wavelength lambda of the electron is lambda is equal to h upon under root 2 MeV is equal to 1.227 upon under root V Nm. Equation 3. For a 120 volt accelerating potential gives lambda is equal to 0.112 nm. This wavelength is of the same order as the spacing between the atomic planes in crystals. This suggests that matter waves associated with an electron could be verified by crystal diffraction experiments. An electron, an alpha particle, and a proton have the same kinetic energy. Which of these particles has the shortest de Broglie wavelength? We have lambda is equal to h upon under root 2 mk. For the same kinetic energy k, the de Broglie wavelength is inversely proportional to the square root of their masses. Alpha particle, being heaviest of the given three, has the shortest de Broglie wavelength. Just as the photoelectric effect demonstrated the particle nature of light, the Davison-Germer experiment showed the wave nature of matter, thus completing the theory of wave-particle duality.